Now, going back to our eigenvalue problem, which resulted from substituting the assumed solution. The eigenvalue problem was k minus lambda m, this matrix times the vector x equals 0, and we said that the only possible way to have a solution for this set of homogeneous equations is to set the determinant to 0, and we did that, and we got 3 values for lambda. Now, for each value of lambda, the determinant is 0, and I can find a solution for the vector x. So, for example, if I start with lambda 1 and substitute the lambda into this system here, I would have the following: k minus lambda times m, and here k was 20 minus lambda, which is 1.453 times m1, which was 1, and here we had negative 10 minus 0 and a 0 over here, and we had negative 10 over here, and 20 minus 2 lambda. 2 times lambda is 2.906, and we had negative 10 over here, and we had a 0, we had a negative 10, and we had 10 minus lambda times 1, 4, 5, 3, this matrix times x1, x2, x3 equals the 0 vector. So now I have 3 equations. Again, expand these equations, this set of equations. I will have 5, 4, 7, x1 minus 10, x2, this should be capital X, x2 equals 0, and then negative 10 x1 plus 17.094 x2 minus 10 x3 equals 0, and negative 10 x2 plus 8.547 x3 equals 0. So now I'll try to solve these 3 equations for x1, x2, x3. Now these are a set of homogeneous equations, so I should expect an infinite number of possible solutions. So if I start with equation 1, x2 is going to be 1.855 x1, and then I can substitute x2 into equation 3 and solve for x3. Equation 3 and solve for x3, which is going to be 2.170 x1, and finally substituting x2 and x1 into equation number 2. If I substitute for x2 1.855 and solve for x3, I will also have x3 equals 2.170 x1. So all solutions will be related to x1, and that's an infinite number of solutions. For each value of x1, I will have certain x2 and x3. So the solution x can be written as x1, and x2 is going to be 1.855 x1, and x3 is going to be 2.170 x1. For each assumed value of x1, I'll have a vector x. So if I factor out x1, and the x solution becomes 1 and 1.855 and 2.170. And instead of x1, I will call this a. If x1 for any value of x1, arbitrary value of a, the solution is going to be 1.855 and 2.170a. Now, these are the three amplitudes of motion of the three masses. This was x1, x2, x3, and recall that the assumed solution was q equals some x cosine omega t plus phi. So the x vector is the amplitude of the motion, and since these three amplitudes are related, we will call this the mode shape of motion. The mode shape means that if x1 moves with an amplitude of 1, then the amplitude of motion in x2 will be 1.855, and the amplitude of motion for x3 is 1.70. These are the amplitudes of motion, and the frequency of motion is going to be, these amplitudes were determined for lambda 1, so the frequency is going to be omega 1, which is 1.206. Now, I will repeat this process for each value of lambda and find the mode shape or the solution for the vector of amplitudes for each value of omega. So for lambda 2, I'll substitute lambda 2 into this matrix and solve for x, and lambda 3 and solve for x. So for lambda 2, solving for the x vector, I'll get this solution, assuming that x1, any random value of b, then the solution will be as a function of x1, 1.590, and negative 1.481. And this means that if the response is omega 2 or lambda 2 at this frequency, then the amplitude of motion, if x1, if the mass 1 moves with an amplitude of 1, then x2 will move to the right with an amplitude of approximately 0.6, but x3 will move in the opposite direction with an amplitude of negative 1.5 approximately. So the shape of the motion will be that these two masses will be moving to the left, and mass 3 will be moving to the right. This is why, again, this is called the mode shape, the shape of the motion. Also for lambda 3, it is another mode shape, another way of possible motion, which is that if x1 is moving in this direction, then x2 will be moving in the opposite direction, and x3 in the same direction as x1, with these ratio of amplitudes. Now, these three values for lambda, since this is an eigenvalue problem, the lambdas are known as the eigenvalues. Okay. Lambda 1 and lambda 2 are the eigenvalues. And the vectors x1, x2, and x3, these three vectors are known as the eigenvectors. So this vector here and this vector, these are all known as the eigenvectors. So if I name these eigenvectors as, let's call this vector vector p1, and this vector p2, and this p3, the three eigenvectors. So I know that the possible solutions, possible responses for the system Q will be either at frequency 1 or 2 or 3, or in the most general form, it will be a combination of all three possible solutions. So I can write this as a combination. For the first frequency, A times P1, that's the vector X, A P1, times cosine, and the frequency of the response at P1 is omega 1, which is 1.206 T plus some phase angle phi1, plus the other possible solution is at the frequency 3.746. So the B P2 cosine omega 2 is 3.746 T plus phase angle phi2 associated with omega 2, and C P3 right here times cosine the third frequency, which is 4.951 T plus phase angle 3. So this is the most general form of the natural response of this system. We have three unknowns, or three coefficients A, B, C, and three phase angles, and these 6 values can be determined by the initial conditions, to just like we did for the second degree freedom system. For each second order differential equation as an initial value problem, you need 2 initial conditions. Here you have 3 differential equations, so you need 6 initial conditions, and the initial conditions will be x1 at 0 and x2 at 0 and x3 at 0. These are 3 initial conditions, and the other 3 initial conditions is the velocity, initial velocities x1 and x2 and x3. 6 initial conditions, substituting into this general response x1, x2, x3, and the Q is x1, x2, and x3. Substituting these 6 initial conditions, I will end up with 6 equations. Solve these equations for the 6 unknowns A, B, C, and phi1, phi2, phi3. And that's the natural response for a multi-degree freedom or multi-mode system. And now this is where the name multi-mode comes. We have 3 modes of motion, 3 mode shapes, 3 modes of motion. The mode of motion is refers to the motion of these 3 masses, the shape of the motion. The first mode, the 3 masses move together in one direction. The second mode, 2 masses move in one direction, and the third mass moves in the opposite direction. The third mode, the first and third mass move to the left, and the M2 moves to the right.